I'm recording. Okay, thank you. Okay, let's get back to optimization. Okay, so let me just give you a very simple problem. So simple, you know the answer right away. First example. Okay, what is the answer? X equals to what? So F is minimized. Anyone? 0, yes. So we usually write in this way. When you have a star, that means optimal design. Okay? Very good. Thank you. Another example, minimize f of x equals to x minus 3 squared. Okay, so what is the optimal? Anyone? Very simple. Yeah, so easy. Someone already feels like I'm giving stupid questions. Okay, how about this? Minimize f of x1 and x2 equals to x minus 4, x1 minus 4 squared plus x2 plus 6 squared. How about this? Also very simple. You can write in this way. Yeah, let me know. What's the answer? Yes, so easy. So see, you know how to do optimization. If you know the mathematical function, that's optimization. Okay, another example. Minimizing f of x equals to, let's use the same problem. Do we use the same problem? Let's use sure, same problem. But this time I'm putting a constraint here. So there's a limitation. You need to satisfy the constraint and at the meantime find the optimal. Okay, so I'm trying to find a constraint. How about x1 must equals to 3. How about this? Anyone? So what is optimal? It's a vector at the end. So what is the optimal for x1? Yes, you're right, because the constraint says x1 must be 3. So what is the optimal for x2? x2. Yes, so the same. Yes, exactly. So now I'm going to make it more advanced. You probably cannot visualize it easily. So let's try x1 plus x2 must equals to 10. So this time nobody can observe the answer. How? Right? Then it's very hard. So in mechanical design or optimization design, usually the functions are not that simple. So it's not like, okay, you observe and then you know the answer. But if you have a problem in like this, two variables, you can make a drawing. Let me show you. Maybe do it like this. This is x1, this is x2, okay? I'm trying to draw so-called the contour. I'm trying to draw the contour of f of x. What is the contour? Something like this. Contour lines represent values with same height or same value. So contour lines represent locations with same value. Okay. So where do you usually see contour? On the weather forecast, like a high pressure, low pressure, or on the geographical height distribution. For example, this is Taiwan, this is China, Japan, Korea, and usually you see, okay, high pressure contour, low pressure, right? These are so-called the contour. So every line represents same level of pressure, okay? So over here, we are using contours to represent how the function looks like. So what's happening is, here is 4, and -6 is right here. So this is actually the center of the contour. So the contour actually looks like a circular shape. Okay. So this is where f equals to 0. This is where f equals to 1. This is where f equals to 4. How do I know? Because if you plug in a point, for example, you plug in this point. This point is 3 and -6. If you plug in, that would be -1 squared plus 0 squared. So that's 1. If you move to here, that will be 2 -6. Sorry. So that ends up with -2 squared plus 0 squared. That's 4. Right? So they are contour lines with same function values. Now, let me draw the constraint x1 plus x2 equals to 10. That means I need to find where is 10. For example, if this is 10 and this is 10. So this line actually is x1 plus x2 equals to 10. Okay? So where is the solution? If you are able to observe this shape of the objective function, the solution is right here. Can someone recognize it? It's like a 45-degree toward the upper right corner. Why? Because if you keep on drawing this contour, right? When you have tangent contact with that straight line, that's where you have contact with the straight line, the first time you have contact. And for example, if this is a value of, for just example, for example, 1000. And if you draw another contour a little bit further, this could be something like a 1500, could be something higher. So on the green straight line, that contact point has the smallest function value. So on that green line, there's only one point that has the smallest function value. That is your optimal design. Okay, so maybe someone can observe this, maybe some of you cannot. That's okay. Not every problem can be solved by this kind of graphical way. There is actually mathematical way to solve this problem, but it requires a lot of mathematical derivation and solution process. And you may need to take my graduate course in order to understand this. So I'm not going to spend too much time on this, okay? I just want you to understand there is something called constraint functions, and you are inside this design space. You're trying to find a solution constraint and minimize your objective function. Okay, let's play with math and talk about a different problem. Number 6. This time, I want to have easier objective function. But for the constraint, I would like to say, sorry, x1 plus x2 must be greater than 10. Okay, and then maybe something like x2 equals to 1/2 of x1, maybe plus 3. Okay, something like this. Okay. Again, you probably cannot observe what is the solution, but I can use the graphical way again to show you where the solution is. Okay, let's begin with the graphical approach. Here is x1 and x2. And just like what I showed you earlier, I can draw the contour of the objective function. So they are circles. Okay, so this is the contour of f of x. Now, I use 10. Now let me change the value. I don't want to use 10 anymore. Change it to a smaller value. Let me change it to 3. So in this case, I can draw another contour. And here's 0, 3, and 3, 0. If I draw a straight line passing through those points, those 2 points, that's actually representing this equation. However, this time I'm not using equality, I'm using inequality. This means inequality. So 1/2 of the design space is good design. The other half is not. So over here, entire area over here, not satisfying. Not satisfying. X1 plus X2 greater than 3. Sorry. We call this infeasible space or infeasible region. So inside this space, there's no solution because we want X1 plus X2 must be greater than or equals to 3. So on the other hand, the other half right here, including the green line, satisfies X1 plus X2 larger than 3 or equals to 3. So we call this yellow space, including the green line, we call it, we call it feasible space. What does feasible mean? Feasible means acceptable or acceptable, allowable. Okay. So we can only find our solution in the yellow region or on the green line. How about the other constraint here? Let me try a different color. This color. So to draw this line, I need 0.3 here and 1/2. So this purple, I should say maybe pink or magenta, or let me call it pink. This pink line is actually this one. This one. Okay. So I must stay on this line because there's an equal sign here. It's an equality constraint. Now, can someone tell me what is the solution? I can already see it. Yes? Yes. Really good. This is the optimal. This is the optimal. 0 and 3. Yes. This is the optimal. So sometimes graphical way helps you to find it, but you need human observation. Okay. I would like to introduce one simple method that finds the optimal mathematically, not by graphical. But in order to find the optimal mathematically, I can only use single dimensional problem first. So let me introduce you something called the Newton's method. So Newton actually created this method. So this can only be used for so-called the unconstrained minimization problem. What does that mean? For example, minimizing f of x. So over here, we are only solving one dimensional. One-dimensional. What does it mean? One variable, basically. So let's say I'm solving x squared minus 5x sorry, plus 10. Okay, something like that. So in Newton's method, the procedure is like this. I need to have an initial gas. And we're going to iteratively solve it. There's a terminology called iteration. What is iteration? Iteration is like, make sure no one is talking. Any, Peter, any message from the student? No? So far good? Okay. If there's a message, let me know. So what does iteration mean? Iteration is like you repeatedly redesign your problem. And every time you repeat, it's like a one iteration. Okay, so it's like a repeatedly redesign your model. Okay, and every time, every redesign is like one iteration. Okay, so sometimes we want to use a number to represent how many times you retry. So we define k equal as the iteration number. Okay, and we start with k equals to 0. So over here, the initial gas, we will say xk equals to 0. We usually put a bracket and write the iteration number in the bracket and put the bracket in the superscript. We can have an initial gas, for example, 10. Just random guess. And then what do you do next? Newton's method, 1D Newton's method, will ask you to solve the following. You need to tell me what is f prime, f of x of k, and f double prime x of k. This is what Newton's method needs. Okay, so let's try it. Let's now try it. F prime equals to 2x minus 5. F double prime equals to 2. So in our particular case, this is 2, and this is 2 times our current design is 10 minus 5, that's 15. Okay, so what's next? In Newton's method, there's an equation. Xk plus 1 equals to xk minus f prime of xk over f double prime of x. So Newton's method asks you to solve for this and using this new number to update the next design variable. So let's try it. Our previous guess was 10 minus 15 over 2. So at the end, it's like 2.5, right? So xk plus 1 is 2.5. That's what Newton's method tells me. Next, there's a very important procedure, something called the convergence check. You need to check if the procedure converged. How do you check? You will calculate the new design minus the previous design, take absolute value, basically the difference between the current design and the previous design. You want this difference to be small, very small. So let's say 10 to the negative 3. I call this termination criteria. So if this is satisfied, I will terminate my iteration process. Or I will say the optimization process converged. Okay, so if converged, if yes, then converged. Then the latest one, oh, I should do this. Your optimal design is your latest solution, okay, latest design point. If not, we are going to go back to here. Just like what we said earlier, it's like the process of redesign. We're going back to here. But when you go back, you want to upgrade your iteration number by 1. K equals to K plus 1. That's all. Let me show you what's going to happen. So let's review the optimization process again, the Newton's method. So initial guess, right? This is your initial guess. And then, oh, sorry. K equals to 0 at the beginning. And then you want to evaluate f prime of xk and also f double prime of xk. You want to evaluate both numbers because that's what Newton's method asks you to do. Later on, Newton's method tells you the new design point should be determined like this. Just trust Newton, use this equation. Okay, and then we said the convergence check. Usually, if there's a check, it looks like this, right? And if yes, then your optimal is your latest design. If no, it goes this way. No. So when you go up, K equals to K plus 1. So this is a optimization procedure, a mathematical procedure for finding the minimum point using Newton's method. And earlier, I already showed you one example. Now I'm going to continue the procedure to prove I got the solution. So earlier, I was here. My original design was 10. My new design was 2.5. So the absolute value gives me 7.5. It's larger than this small value. So not converged. So if it's not converged, I need to go back to here. I need to follow the procedure. K equals to K plus 1. Earlier, K is 0. Now, K becomes 1, right? So now K becomes 1. So in the second round, I'm going to use a different color. I use this pink color. In the second round, F double prime is still 2. F prime equals to, I need to move a little bit. F prime equals to 2 times the current x. Here I need to use x of k equals to 1, right? I need to use this value because over here, 2x minus 5. I need to plug in the current one. The current one is 2.5. So I plug in 2.5 minus 5. So that gives me a number of 0. So using those, my new design, x of k now is 1 plus 1. So I have k x of 2 equals to the previous one minus f prime and f double prime. And this is actually 2.5, the previous one, minus 0 over 2. And at the end, it's again, same answer, 2.5. So now when I do a convergence check, my previous one is 2.5, my new one is 2.5. So at the end, 0. It's actually smaller than to this small number. So converged. At the end, x star actually equals to 2.5. Okay? So I don't even try to draw a picture of this. I didn't try to do something with it. I just follow Newton's method and see what it gives me. Okay? How about two variables? How about two variables? When you have more than two variables, it's more complicated. Do you want to learn how to do it? Anyone interested in two variables? No? No? Say again? Too boring? Oh, you want to see it?
Yeah.
Oh, okay. Sure. Let me show you the magic, okay? Just treat it like a magic show. Okay? Now, two-dimensional Newton's method. Okay, let's try it. So, I need to formulate a problem, minimizing, let's say, x1 squared plus 10, x2 squared minus 5x1 plus 6x2 minus 29, something like this. Okay. Of course, if you had the earlier experience, you know the answer is 5 over 2 and negative 0.3. You can observe it because it's a polynomial. But let's do not do this. Let's just trust Newton. So let's have an initial guess. So this time, everything is a vector, okay? And iteration number starts with 0 again. Now, I just want to have a random guess, 2 and 2. How about this? I don't know the answer, I just try 2 and 2. Any number works. So, in 2D, it becomes more complicated. The next step, you need to solve for two things. One thing is called the gradient. This is called the gradient. And the other thing is some person's name, Asian matrix. Like an H. Okay? So what's inside gradient in Asian matrix? So in gradient, what you need to do actually is partial derivative. Partial f, partial x1, partial f, partial x2, and plug in whatever you have. Plug in, okay? Don't be scared by math. It's actually not very difficult. Let's try this in our objective function. Partial derivative is not difficult. It's like a 2x1 plus 20. The other one is negative. Oh, sorry, I made it wrong. 2x1 minus 5. Here, this is where you have x1, right? Over here, 20x2 plus 6. That's exactly the gradient matrix you have for this problem. How about Bayesian matrix? Bayesian matrix covers all the second order derivatives. Let me show you. Second order partial derivatives. Don't be scared by the math again. It's not difficult. It's just looking scary. Okay, it's the container that includes all the possible second order derivatives. And let's try to write down how it looks like. In our case, it's gonna be another partial derivative with respect to x1 for this, so it's 2. The other case, partial derivative of x and then derivative over x2, so that's 0. So x2 first and then x1, x2 first and then derivative over x1, so that's 0. Derivative with respect to x2 twice, so that will be 20. Right? So the value comes from here. Oh, sorry. I should go back. The numbers comes from here. 2 and 20. Okay. So what's next? So what does Newton's method tell us to do this time? It's a vector this time. X of k plus 1 equals to x of k. Now, it's a little different. Bayesian matrix inverse dot product with the gradient vector. Don't be scared by this again. Don't be scared. It's not scary. F of x at this time is 2 and 2, right? Bayesian matrix is 2, 0, 0, 20, and then inverse. Dot product with the gradient, plug in. So 2 times 2, 2 times 2 over 5, 20 times 2 plus 6. It's basically this. And let's solve it. This is gonna be 2 and 2. And for this particular case, if you inverse it, it's 1 over 2 and 1 over 20, actually. You don't really need a complicated equation to find the inverse of this one. This is an easy one. And then the product with 4 minus 5, negative 1, 40, so 46 here. Okay? So let's try to get the real number. So it's gonna be 2 minus plus 1/2, 2 minus 46 over 20. Okay, so at the end is 5 over 2. This is gonna be 20 negative 6. So it's gonna be, sorry, 5 over 2 and, right? Now, remember for Newton's method, you need to do convergence check. What do you check this time? The new design or minus the previous design. But this time, because one vector minus another one equals to a new vector. How do you do absolute value for a vector? You can't. So we can only use, this is so-called the norm. What is the norm of a vector? For example, this is a vector A, B, and C. Norm of a vector basically is the length of the vector, square root A squared plus B squared plus C squared. That's the norm, okay? So you can calculate the norm of this difference vector. And you want this length to be small enough. So you want to check whether it's satisfied or not. If not, what do? Go back to here. And again, k equals to k plus 1. So if not satisfied, how about yes? If yes, then your optimal is your latest design. Okay? So overall, let me show you the procedure again, the overall procedure. You have initial gas, k equals to 0, and you need to compute the gradient of f, plug in x of k, you need to compute the Hessian matrix, plug in x of k, that's what you need to compute. And then you need to get the new design point by the equation provided by Newton's method. Not G, yes. And then you want to do convergence check, right? Convergence check. Question mark. Okay, if not converged, goes up to here. The redesign process. If yes, this is no, this is yes, then your optimal is your last one. That's the general procedure. Okay? So in the earlier design, let's try to put in numbers. So for the convergence check, I had 2.5, negative 0.3, minus 2 and 2, right? I'm pretty sure the resultant vector has a length greater than 10 to the power of negative 3. So I'm pretty sure it's larger. So not converged. I'm pretty sure I don't even need to calculate it. It's not converged. So now I need to go back to here, up to here. So this time k equals to 0 plus 1. K now is 1. Okay? So when I compute, I need to calculate the gradient vector. So I will have 2 times the x of k equals to 1. I need this. I need this value. It's actually this guy, right? 2.5 and negative 0.3. This is the solution at k equals to 1 here, right? So I plug in 2.5 here, 20 times 0.3. I need a negative sign in the front, minus 5 and plus 6. Did you notice it becomes 0 and 0? Okay, that's a magic show, right? That's the magic. So when you plug in Newton's method in the second round, the x2 equals to the x1, which was 2.5 minus 0.3, minus the inverse of Hessian, 1 over 2 and 1 over 20. Subproduct with the gradient now is 0, 0. So at the end, of course, is the same value. Same value. Okay? And when I do convergence check, of course, 2.5 negative 0.3 minus 2.5 negative 0.3. This is gonna be 0, so converged. So at the end, the solution is 2.5 and negative 0.3. So if you really want to find the solution with two variables. Okay, let me see the time. Now it's a 2:48. I think we can take a short break. Later on, I want to talk about something called the design of experiments. Okay, that's also an important part in besides the optimization. Okay, so let's take a break, 10 minutes.